right, today we have to talk about the wave equation. As a reminder, here's what the wave equation looks like. A squared times the second partial of u with respect to x. Here's where it changes from the heat equation, is equal to the second partial of u with respect to t. With the heat equation, it's just the first partial of u with respect to t. Remember that we are going to say x is between 0 and L, and t is going to be positive. Our two boundary conditions are that u of 0t is equal to 0, and u of lt is equal to 0. And then we have two initial conditions, not just one. The first one is u of x comma 0 equals f of x. And then the second one is the first partial of u with respect to t at t equals 0 is equal to g of x. So before we actually solve this, I want to make sure we know what all of this means. We are looking for the solution u of xt. What does u of xt represent? Vertical displacement, right, from the x-axis to the string at some point in time in some spatial dimension. What are these two conditions telling us?
The ends don't.
More specific.
They're on x. They're fixed.
Right. The two ends of the strings are fixed to the x-axis. Those two conditions are what make this equation homogeneous. So currently, we're always going to be looking at a string that is tethered on both the left and the right side to the x-axis. What is this? Rachel?
Okay, it's the initial vibration of the displacement.
Yeah, the initial displacement. And then what is that condition? Initial velocity. Okay, so now that we got all that down, if we're going to solve this, what would your suggestion be? Come on, guys. We only have one solving method. Let's try separating. Okay. So we're looking for u of xt. We're assuming that it's going to be the product of two functions, one of x and one of t. If we plug that into our equation, then we get a squared x double prime t equals x times t double prime. Remember, these are not variables x and t. Those represent functions of x and t. So we're going to separate. We end up with x double prime over x. I'm going to leave the a squared with the t side. We're going to set this equal to negative lambda. This then is going to end up giving us two different equations. We end up with x double prime, add lambda of x equals 0. And t double prime, add a squared lambda of t equals 0. Okay, do you remember what we did next then after we had our two equations? We looked at the three cases. And what else?
Don't we want to find non-trivial
Right.
solutions?
So how do we find the non-trivial? What do we got to look at? Yeah, the boundary conditions. So let's look at the conditions first before we consider the three cases. So we're looking at the boundary conditions, not the initial ones. So first we have that u of 0t equals 0, and we have that u of lt equals 0. If we look at this first one, that tells us that 0 is equal to x of 0 times t of t. And then we said it would be trivial if t of t was equal to 0, because then u would always be 0. So this really tells us that x of 0 equals 0. This will be a similar idea. 0 is equal to x of L, and then t of t. Again, we don't want t of t to always be 0, so this gives us x of L equals 0. So then here's what we have for the x equation. We have that x double prime add lambda of x equals 0 with the conditions that x of 0 equals 0 and x of L equals 0. And then like Helen said, I think it was Helen, that there's going to be 3 cases that we're looking at. Helen, was that you?
I said non-trivial.
Margot, were you the one that said 3 cases?
Yeah.
Okay, there we go. So as Margot reminded us, there's going to be 3 cases. First case is where lambda equals 0. Second case is where lambda is less than 0. Third case is where lambda is greater than 0. If you recall from the notes we took in 12.3, only one of those is non-trivial. Which one is non-trivial? First, second, or third case? Third case. So this is the only one that's non-trivial. These two are both going to be trivial. And that's always going to be the case. Okay. So we want lambda to be positive, so we're going to call lambda alpha squared. We then end up with x double prime add lambda squared x equals 0. I'm going to skip a few steps and just tell you that x of x then ends up being c1 cosine of alpha x add c2 sine of alpha x. So that's something we already did in 12.3. If you don't remember, go look back at it. And then we have those 2 initial conditions. First one being that x of 0 equals 0. If we plug that in, we get 0 equals c1, add 0, which tells us that c1 equals 0. And then we have that x of L equals 0. So for that, we get 0 equals c2 sine of alpha times L. We don't want c2 to be 0 because then that would be a trivial solution. So instead, we want alpha L to be equal to n times pi. That's when sine would be 0. So we get our alpha then to be n pi over L. N being 1, 2, 3, etc. That tells us that our alpha, or our lambda rather, is n squared pi squared over L squared. So finally, we get x to be c2 sine of n pi over Lx. Now, does that look familiar? It definitely should. Okay, that was just x. Now we have to do t. T, as a reminder, is t double prime, add a squared lambda times t equals 0. So with this then, we get m squared, add alpha squared, lambda equals 0. M then ends up being plus or minus a times the square root of lambda times I. Remember, that's because we said that lambda is going to be positive, so this entire quantity is positive, which is going to give us the imaginary roots. This then will be plus or minus a. Lambda we have up here, so times the square root of n squared pi squared over L squared I, which is just plus or minus a times n pi over L I. So our solution t then is going to be c3 cosine. This I'm going to write as n pi a, so n pi a over L t plus C4 sine of n pi a over L t. Okay, so here's where we're at now. Ru is going to be x multiplied by t, which in this case is going to be C2 sine of n pi over Lx multiplied by all of that t. That's not normally how it's written though. This is not really the most helpful way. That's because we have all these constants. Now if I multiply those two constants, it's going to give me another constant. When I multiply C2 and C3, I'm going to call that AN. So that's going to be AN cosine of n pi a over L t plus B of n sine of n pi a over L t. And then generally that sign is left to the end. Okay. So at this point, we decided we need to find some expression to find A of n and some to find B of n. And do you remember how we used the superposition principle? We said we're gonna plug, well, I'm telling you right now, we're going to plug in n equals 0, we're going to plug in n equals 1, we're going to plug in n equals 2, we're going to sum them all up, right, to infinity. That would give us all the terms. Okay, so this is what we're going to do. I'm going to take the summation from n equals 1 to infinity of all of that. Right, wouldn't that give me every single term?
Yeah.
Okay, bless you.
Thank you.
Okay. At this point, we still have two conditions we have not used yet. The only conditions we've used are the boundary conditions. We have not used the initial conditions. So the initial conditions we had were u of x0 equals f of x. So the initial displacement. And then we had the partial of u with respect to t at t equals 0. That gives us g of x. That was the initial velocity. So let's start with this one, the initial displacement. We have u of x0 is equal to f of x. What we're going to do is we're going to plug in 0 for t. We plug in 0 for t up here. Sine of 0 will be 0, so that'll go away. This will just be 1. So we end up with the summation from n equals 1 to infinity of a of n sine of n pi over Lx. That should look familiar. What is this?
Half range equation.
This is a half range expansion. For f in a sine series. In this case, x being between 0 and L. So what we get then is we get a of n from the half range expansion is going to be 2 over L, the integral from 0 to L of f of x sine of n pi over Lx dx. Okay, so we're almost there. Last thing we need to do is we need to find an expression for b of n. So to find b of n, we're going to use that last condition we haven't used yet. So that's going to necessitate us taking the first derivative of u with respect to t. So I'm going to write u one more time before I take the derivative. Okay, so I'm going to differentiate this with respect to t. If I differentiate the first term with respect to t, I'm going to end up with negative a of n times n pi a over L sine of n pi a over L t plus b of n cosine of n pi a over L t. Sorry, I missed something here. This should be b of n times n pi a over L cosine of n pi a over L t. And then that last term at the end, sine of n pi over L x. Okay. We are interested in, though, the derivative at t equals 0. That's what we're going to do next. We're going to plug in t equals 0. If we plug in t equals 0, sine of 0 will be 0, so that whole term goes away. If we plug in 0 here, we're going to end up with 1. So we end up with b of n times n pi a over L, and then that sine of n pi over L x. And all of that is equal to g of x, because that was the condition. Promise we're almost there. Do you guys notice how this is close to the half range expansion for sine? Like if I took away that, it would be the half range expansion for sine. Okay, so half range expansion for sine. Normally this part is b of little n. So you have b of n times sine of n pi L over x. So b of n then, which is big B of n times n pi a over L. For the half range expansion for sine, that's 2 over L times the integral 0 to L of g of x sine of n pi over L x. So what we're going to do then is move all that over to the other side. So you get b of n to be 2 over n pi a integral 0 to L of g of x sine of n pi over L x dx. That's our final solution. So we're going to write it one more time so that everything is all in one spot. Final solution, u of xt, is going to be the summation from n equals 1 to infinity of a of n cosine of n pi a over L t plus b of n sine of n pi a over L t times sine of n pi over L x where a of n is 2 over L integral 0 to L of f of x sine of n pi over L x dx, and b of n is 2 over n pi a integral from 0 to L of g of x sine of n pi over L x. Okay, any questions before we do an example? No? Okay. So we have one example to do, and then we have a superposition principle to do. We're going to do the example first. Okay. We are going to find u of xt if the string below is released from rest. And then we have a picture. First thing we need to do is we need to write the equation. So we need to write the equation, we need to write all the conditions. So here's the general wave equation. Okay, we need our two boundary conditions. So we see that our string is attached to the x-axis here and here. So we get u of 0t equals 0 and u of lt equals 0. That means we're tied to the x-axis. We also know that the string is released from rest. So that tells us that the partial of u with respect to t at t equals 0 is in fact 0. So the initial velocity is 0. This, remember, in the previous problem, that's what we call g of x. And lastly, we know the initial displacement, u of x0, is equal to f of x. This one we're actually going to have to find. So this is our initial displacement. So it's going to be piecewise. We're going to need to find both equations. So there's going to be one equation when x is between 0 and L over 3. And there's going to be another equation when x is between L over 3 and L. Okay, this point up here is L over 3 comma h. Now, you all can find the equation of this line if I wanted you to, right? And the equation of this line if I wanted you to? Okay. Do we need to go through finding the equations of the lines?
No.
No, so I can just tell you what they are. Perfect. This one is 3h over L times x. The bottom one is 3h over 2L times the quantity L minus x. Okay, we're going to have to find A of n, and we're going to have to find B of n. Which one is going to be easier to find in this case? B of n. What is B of n? 0. Right, g of x is 0, so B of n is going to be 2 over n pi a integral 0 to L of g of x sine of n pi over Lx. G of x, though, we said was 0, so B of n is really 0. So A of n is the one that we need to be more concerned about. Okay, A of n. We have 2 over L, and then the integral 0 to L f of x. In this case, we're going to have to split that up. So we have the integral from 0 to L over 3 times 3hx over L sine of n pi over Lx dx. And then add the integral from L over 3 to L of 3h over 2L, the quantity L minus X, sine of n pi over L x dx. Okay, here's what I chose to do when I did this problem, and you guys are going to do the same thing I did just so that I don't get lost. I'm going to do this integral first, simplify it as much as I can, and then I'm going to do this one. Are we okay with that? Okay, here we're going to have to do tabular, so we have 3hx over L, and then 3h over L, and then 0. Remember, everything is with respect to x. Over here we have sine of n pi over L x. So then negative L over n pi cosine of n pi over L x. Negative L squared over n squared pi squared. Sine of n pi over L x. So this we're adding, this we're subtracting. So this ends up being 2 over L. And then the quantity, these L's are going to cancel. So negative 3hx over n pi cosine of n pi over Lx. One of those L's will cancel. So plus 3hl over n squared pi squared sine of n pi over Lx. All of that from 0 to L over 3. Okay. So now, plugging in, we get negative 3h times L over 3 over n pi cosine of n pi over L times L over 3 plus 3hl over n squared pi squared sine of n pi over L times L over 3. If I plug in a 0, because of this x, that whole quantity will be 0. Sine of 0 is also 0. So the 0 doesn't get me that far. Okay. So this then will be 2 over L. A little bit of simplifying will give me negative HL over n pi cosine of n pi over 3 plus 3hl over n squared pi squared sine of n pi over 3 okay. That was the first part. We still need that second integral. The second integral, so this one up here, I'm going to pull this whole quantity out in front because it doesn't have an x in it, so I can do that. So that one is going to be 3h over 2l, integral from L over 3 to L minus x, sine of n pi over Lx dx. Again, we are going to have to do tabular. So this is L minus x, negative 1 and 0. So adding, subtracting. Okay, so that one, I still have the 2 over L. I have the 3h over 2L that I pulled out. And then I have negative L times L minus x over n pi, cosine of n pi over Lx, subtract L squared over n squared pi squared, sine of n pi over Lx. All of that evaluated from L over 3 to L. Okay. Guys with me? Okay. Those 2's are going to cancel. So we end up with 3h over L squared. If I plug in L here, I'm going to end up with a 0. If I plug in L to sine, I'll get sine of n pi, which is going to be 0. So this is where I really need to start. Now remember, because it's the second one, we would be subtracting, so it's going to flip all the signs. So we have L times L minus L over 3 over n pi cosine of n pi over L times L over 3 plus L squared over n squared pi squared sine of n pi over L times L over 3. Okay, so that ends up being 3h over L squared. That will be 2/3 L squared over n pi cosine of n pi over 3 plus L squared over n squared pi squared sine of n pi over 3 Okay, so let's go back to this, which we had before. So that's what we had before. This is what we have now. So I'm going to distribute this, I'm going to distribute that, and then we need to start adding stuff together. So this is going to be negative 2h over n pi cosine of n pi over 3 plus this will be 6h over n squared pi squared sine of n pi over 3 if I go to here, those 3's will cancel, those L squareds will cancel, so I end up with 2h over n pi cosine of n pi over 3. These L squareds will cancel, and I'm going to end up with 3h over n squared pi squared sine of n pi over 3. Now look how nicely that worked out. Those 2 cancel. These 2 are going to end up being 9h over n squared pi squared sine of n pi over 3. Now, there is not an efficient way to change this sign into something else, so we're just going to leave that. So that's our A of n. We already figured out that B of n equals 0. So our final U of xt is the summation from n equals 1 to infinity of 9h over n squared pi squared sine of n pi over 3. So that's just A of n. A of n then is multiplied by the cosine of n pi a over L times t. And then at the very end, we always have that sine of n pi over Lx.
On the test, are we going to have to derive the original general equation that we found? The general solution?
No. So if you have that memorized and it applies to the problem I give you, you do not have to rederive it.
Okay, but then yesterday in our homework, did we have to rederive the equation for any of the problems?
I think there was one that you should have because it wasn't exactly the same as the one we did in class.
Okay.
Rachel?
I know we've done this before, but where did the cosine n pi a over L t be finally answered?
It comes from the equation. A of n is multiplied by the cosine of n pi a over Lt. Right, the previous question was deriving. Example 1 was using that equation. Okay. Anything else before we move on to the last thing that I want to talk about? Okay. Last thing we need to talk about is the superposition principle. Here's the idea with the superposition principle, is that you can solve a wave boundary value problem by solving two hopefully easier boundary value problems. Not always going to be easier, sometimes it will be though. So here's the original boundary value problem that we had. It's exactly the same one that we wrote at the original class, or at the beginning of class. Okay, so what we're going to do is we're going to solve one equation that involves f of x and one equation that involves g of x. So here will be your problem 1. Sorry, these should all be U1s. So the basic idea is for the first equation, make g of x 0, but keep f of x. Second equation, sorry, this should be a 0. Second equation, make f of x 0, keep g of x. Then your solution, u of xt, will be those two solutions added together. So it'll be u1 of xt, which you got from the first problem, add u2 of xt, which you got from the second problem. Now, this is only going to be helpful if you have an equation that has both a function for f of x and g of x. The example that we did, g of x was 0. This is not necessary then. Not necessary, not even helpful. So I believe there's one in your book where you have both a function for f of x and g of x. You can use the formulas exactly the way we have them, or you can use the superposition principle. Okay, do you want me to tell you why this is the case, or are you just gonna accept it? It's not a proof. Do you want to know why, or you just accept that that's the case? You don't have to write this down, but it's probably good to know, or good to see. So let's just verify that the boundary conditions and that the initial conditions are still going to work. Our u of 0t, then, based on this equation, is going to be u1 of 0t, add u2 of 0t. u1 of 0t is 0, u2 of 0t is 0, u of 0t, or 0t is 0. With me? Likewise for u of lt. u of lt is 0. That'll give us 0 plus 0. So those are the boundary conditions. If we look at the initial conditions, u of x0 is u1 of x0 plus u2 of x0. u of x0 is f of x. So we get f of x equals f of x plus 0. Get the idea? Questions on the wave equation?